Hi, Chris Kuzmal here. We're going to talk about how to implement the biconditional method and possibly the others in detecting a complex logical sentence. But before we do that, let me just point out the bug for negation here. This substring of 1 is going to be a problem if S is an empty string. And so that's the scenario where you could have a problem. You'll need to check for it. That's why there's this blank space here. You need to see if S is too short. Here we have that actual biconditional code. In that actual biconditional code, let's just read off what happens to it. The first thing we do is we determine what's called the left part end index. And so there's another method, which we haven't talked about yet. It detects where a particular string is in another string. So if we have this biconditional somewhere in our sentence, then the left part index will indicate where it is. We'll give the number, the offset into the string of where that is located. And then, of course, 3 spaces further to the right will be where the rest of the logical sentence is. So the left part of the logical sentence of a biconditional will end at this place, left part end index, and the right-hand part of the biconditional will start at right part start index into it. So we have to just use the substring methods in order to extract these 2 portions of the string, but also we have to determine whether or not we even are looking at a biconditional, because we could be getting a pretty random string here. So if the left part index is less than 1, then we're going to return false. And if this thing isn't in there, then the index of method will return -1. So this basically detects that there's no biconditional operator in there. But if there is a biconditional operator in there, then we got to make sure that the right part start index isn't too small. So the right part start index is actually too large. If the right part start index is off to the edge, in other words, there's nothing to the right of the biconditional operator, then we also have to return false. And that's what this line of code is doing. And you might wonder, why is there -1? This is where you will have to do a little bit of exploration, okay, to find out that, and length tells us the length of the string. So finally, this code all sets us up to be able to do what the previous code, which was so much more clean, the left hand of biconditional and the right hand of biconditional, we basically embedded what those helper methods do into our actual method here. And then left part and right part are gotten by doing the substring from 0 up to the left part end index, and substring starting at the right part start index. And guess what? Now we do exactly what our previous code does. We do the conjunction of whether or not the left part and the right part are legal. And that's how the biconditional code works. That's everything for the biconditional code. And even more exciting, this code is virtually identical to the code for the other 3 cases. The only things we need to change are, for the implication code, we replace the biconditional operator with the implication operator, and the length of the offset we're checking for is 2. The rest of the code, it's all identical, completely identical. Same thing for conjunction. I didn't highlight them as much, but the conjunction is a ampersand and the offset is 1. And finally, for disjunction, the offset is also 1 and the operator is a vertical bar. Guess what? That's it. This is a diagram of the entire definition of a legal logical sentence. We get rid of spaces. We determine whether it's simple. To determine whether it's simple, actually, I had spaces twice here. I don't know what's up with that. And then we determine whether or not it has it's of length 1. I guess I meant to write length there, not spaces. And if the logical sentence is complex, then that means that it either begins with a tilde, or it's binary and it has one of these operators in the middle of it. And that's all there is to it. And we have written the code for all of it.